All right, we are finally on. I figured out how to get this going, I think. Are we running? How to get this going? Okay, awesome. Are we running? Okay. Sorry, it took me a while to figure out exactly how to get that all working there. So I want to welcome you guys to our first ever streaming review. All right. So what I'm going to do here is I'm going to start out by going through all the targets. I'm going to read through each one of them, kind of explain a little bit about what's going on with that, and then I will open it up to some Q&A. Let me see, make sure that I've got the little screen that's open here. I'm just going to click on this, and all right. Sorry, it's taking me a little while to kind of figure out how to make this work. Okay. Hey. All right. Cool. All right. I'm seeing some comments there. Awesome. All right. So now I've kind of figured out some of the logistics of how all this stuff works. Let's get on into it. All right. So states of matter target list. All right. So I'm going to just kind of read through it here. All right. So the first one says to describe characteristics of solids, liquids, and gases. All right, so this is the properties of the states of matter. I'll bring up another window here. Okay, so the targets here, it says compressibility, particle motion, volume, structure, shape, and fluidity. Okay, so if you guys remember, we did the very first assignment, something a little like this. Okay. Where I had you guys kind of do a little simulation and you kind of went through all the different states of matter. So for solids, remember solids you cannot compress because they're basically as close together as they possibly can. Now they are moving, so they do vibrate in place. Now they're obviously not moving around all over the place, but they do vibrate in place. As far as their volume is constant, right? That's not changing at all. Same with their structure and the shape, right? You're not changing the structure and shape of a solid unless you're intentionally, like breaking it, okay? But it is a definite shape. And then as far as fluidity, well, obviously solids don't flow. Liquids, so liquids do not compress. And this is one thing that a lot of people kind of get confused. They seem to think that oh, I can compress a liquid, right? Because I can squeeze that water bottle and it changes shape. Well, actually, what you're doing is you're compressing the gas that's actually on the inside of that bottle, because liquids cannot be compressed because, again, their molecules are as close together as they possibly can be. They're just a little bit freer than they are in solids. Okay, so they actually can flow around. Their volume is constant. You're not changing the volume, again, which is why you can't compress a liquid. It's their shape that's not definite, okay? And obviously they're very fluid. Now gases, very compressible, right? Because there's space in between the gas molecules. So they're very free-flowing. They move around all over the place. There's not a definite volume. There's not a definite shape, okay? So pretty much gases, you can do almost anything that you want with that, okay? So that is target number one. Target number two is basically saying, looking at a picture of a solid, liquid, and gas and being able to identify which one it is. And there is an example of that on the test review. I forget exactly which question it is, but it's right on the front of the test review packet, where it's got a picture of a gas and a picture of, I believe, of a solid, or maybe it's a liquid. I can't remember exactly. I forgot to bring it home with me. But so you're going to get pictures just like that on the test tomorrow, and so you're going to have to be able to identify whether it's a solid, liquid, or gas based on the picture. And then once you've identified it as solid, liquid, or gas, then you can identify the properties of each of them. Okay, so that's targets one and target two. All right, target three says to analyze a heating curve in terms of the energy changes and the phase changes. All right, so let me grab All right, can everybody, all right, I got this right here. So let me draw a quick little heating curve on here. All right, so everybody can see this. All right, here, let me scoot back. All right, here we go. Awesome. Okay, so down here on the x-axis, this is, right, this is energy right here. And then on the y-axis, we have temperature, which, if you guys remember, this is the measure of kinetic energy. So what we're looking at here is this section. Sorry, this is really kind of awkward. So this section right here, this is the solid, this is the liquid, and this is the gas. And then the two flat sections here, these are the phase changes. Okay, so when you go left to right, you're going from a solid to a liquid, right? So that is melting. Right to left, that's freezing. Up here, liquid to gas, that is evaporation, and then gas to liquid is sorry, condensation. And then you remember there's the going from a solid all the way to a gas, that's called sublimation. And then when you go from a gas down to a solid, that is deposition. So basically what you're going to have to look for on the test here is that you're basically going to get a blank heating curve like this. And you're going to have to identify, okay, so solid, liquid, gas, what's happening at the two flat sections, you know, so on and so forth. Now, as far as the energy changes are concerned, sorry, I'm a little brain fart. The three sections where it's solid, liquid, and gas, that is the kinetic energy change, obviously, because you can see that temperature is changing there. The two flat sections right here, this is the potential energies, since obviously since temperature is not changing, which means kinetic energy is not changing, and so then the only other option there is potential energy. Okay, so that's essentially what that is. Before I go any further, okay, so I can see we got a question here. All right, so yeah. Okay, good. You guys are answering some of those questions right there. Awesome. Yeah, so endothermic is absorbing energy, exothermic is releasing energy. So when you are going left to right, this is all absorbing energy, and then right to left, this is all releasing energy. So anything left to right is going to be endothermic, and everything right to left is exothermic. All right. So are there any other questions? Like, you guys type in something right there. Am I going too fast? I don't know, since this is the first time we've done this. I mean, is this working for you? I hope it is. So if you have any questions, you know, please, you know, comment there on the side. I mean, I've got the little screen pulled up here so I can see it. So just, you know, feel free to kind of stop me along the way. Otherwise, I'm just going to keep going with this. Okay. So, sorry, let me kind of change my windows here to make it a little easier for me to see some of the questions going on. All right. Okay, so that is target 3. Let me erase this right here. Target 4 is, I'm sorry, okay, looks like we got a question here. Does endo and exo part going to have to be labeled too? So what you'll see on the test, it will not be labeled for you. In fact, it'll basically just kind of be the basic shape of what I drew for you, and you're going to have to identify solid, liquid, and gas based off of that. And then potential energy changes, kinetic energy changes. So yeah. So basically, to answer your question, yeah, you have to be able to label that on your own, because you're just going to get a blank one on the test. Okay. All right, so next question, or next target is target 4, which says to understand the ideas of kinetic molecular theory. All right, and they're basically just kind of written right there. So there's really not much explanation that's needed, so I'm just going to read them. The first idea is that temperature is the measure of average kinetic energy, which pretty much says it right there, right? temperature is a measure of average kinetic energy. So temperature goes up, that means kinetic energy is going up. Okay. The next one is that atoms are in constant random motion, meaning atoms are always moving, right? They never stop. It's a random motion, meaning that we don't exactly know where the gas molecules are. We just happen to know they're kind of in this general area. The next part of it is that collisions are elastic, which essentially means that there's no energy lost. When they collide and they bounce off of each other, they basically kind of go off in a different direction. Nothing ever changes. Okay. And then the last one is that gases are mostly empty space, which should make sense. That's why they're compressible and all that good stuff. Okay. I see there's a question here about the P1V1 thing. I will get to that, so hold that thought. That is coming up later on in the targets. So I will definitely answer your question on that one. Okay. All right. We had another question here. When in the heating curve, is it potential energy? How do you know? Okay, so essentially what that means is that on the diagonal sections of the heating curve, those are the kinetic energy changes. And on the flat sections, that is the potential energy change. Okay, so hope that answers that question. And yeah, I'll get to the equations. The equations are where I'm going to spend most of the time because I know that's probably the most confusing part. So they're just kind of, I'm going to logically kind of go through everything here, and I will get to the equations a little bit later on. Okay. All right. So target number 5 says to explain how pressure is related to collisions. Okay. Well, that's pretty simple. Collisions causes pressure. That's basically it. Okay. So as the gas molecules are moving around, they collide, they run into each other, and they're going to bounce off of each other, and that's what creates pressure on the inside. Okay. Okay, so we got another question. Yes, there is a video about P1V1, N1T1. That's the combined gas law. In fact, the title of that video is Putting It All Together, the Combined Gas Law. So yes, there is definitely a video there to go over that. So what I do is I explain the equation, I work out a couple problems, and then I give you some more to try to work out on your own. Okay, so if I don't get to it here, there is definitely a video for that. Okay. All right, so moving on. Target number 6, explain and apply the relationship between the Celsius and Kelvin temperature scales. Well, that one's really easy. You take Celsius, you add 273, that equals Kelvin. If you start with Kelvin, you subtract 273 and you get back to Celsius. Okay. Look like we got another question here. How many knowledge questions are there? The non-calculation questions. Okay, this actually, since we got a lot of people asking some of these types of questions, it's probably a good time to talk about this. Right at the end of the school day, as we were copying the test, we actually found a better version of the test. So basically what I had told all of my classes, the format of what I told you guys, that's actually not what we're going to have. We went for a different style, one that hopefully is a little bit easier for you guys. So here is the good news for you. No free response. Okay, we decided to get rid of that. So the test that we've got is 33 multiple choice questions. There are 12 of them which are calculation based, and then the other 21 or more the concept stuff, which is kind of really what I'm talking about right here. Okay. So hopefully you guys are all right. I can see we got some good responses on that. In case you hadn't quite figured out, there's a little bit of a time delay between when I say something and when you guys see it. So that's probably why you're seeing a little bit of a delay there. But yeah, so no free response. It's all going to be on the Scantron. And hopefully that'll make things a little bit easier for you guys. Obviously, there are more questions, but that makes every question worth a little bit less. So they're only going to be 3 1/3 points. So instead of some of them being 3.5 points, some of them being 6 points, everything is like 3 points each, and it makes it a little bit easier. So will there be a curve? Don't ask me that question right now. Let's focus on actually doing a good job the first time around. so that we don't have to worry about the scale. But yeah, there will be a scale, but we always take care of that after we take the test. So let's focus on doing well the first time. Are you banned? No, you're not banned. I can totally see your questions. So there's no banning going on. I'm not doing anything. So I don't know what's going on there, Nintendo man. But anyways, all right. So that being said, okay, let's kind of continue on with our targets. So target number 7, explain how the Kelvin temperature scale relates to absolute zero and its impact on molecular motion. So absolute zero is 0 Kelvin, which is negative 273 degrees Celsius. It is the temperature at which everything literally stops moving. So there's no movement whatsoever, which means there's no volume, there's no pressure, there's no temperature essentially. And so yeah, that Millennium Falcon there in the back, that's pretty awesome. Yes, I got that years ago. I know I'm going a little bit off topic, but you brought it up, and I like talking about it. That's one of my prized possessions back there. It actually took me 13 nights in a row to put that together. Like I came home from work and kind of worked on it for like 2 or 3 hours every night, and yeah, it took me 13 days. But yeah, okay. So STP. STP is standard temperature and pressure, which is 0 degrees Celsius and 273 degrees Kelvin. So that's standard temperature, and then standard pressure is 1 atm. You don't necessarily have to have that memorized, because you will have one of these lovely review or reference charts, and I know it's kind of hard to see with all the glare on it, but yeah, it's all written right there. So you don't have to memorize STP, but you do need to know what it is, right? So it's 1 atm, 0 degrees Celsius. And then essentially how to use it, which basically means that in the question, if it says, okay, so this stuff is happening at STP, then that's basically us saying we don't have to give you the pressure or the temperature, because you're supposed to already know what it is. Okay, so I'll get to some examples of how that works a little bit later on. Yeah, I'm sure they did make a new version of the Millennium Falcon. Since Disney has taken over, everything's new. But that's a whole other topic of conversation, and yeah. All right, so in every question, do you only have to use Kelvin? Yes. Do not use Celsius whatsoever. If you recall from one of the assignments that we did, I think it was the pressure and temperature one, where I gave you some data and then had you basically calculate a constant. When you do pressure and temperature, where temperature is in Celsius, there is no constant. But when you do pressure and temperature, where the temperature is in Kelvin, then yeah, the constant comes out. It's beautiful. So yes, definitely do not use Celsius. You just kind of get in the habit of, you see Celsius, you add 273, and that moves it right on. Okay. How do you change from moles of ammonia to moles of water? Hold that thought. I will get to that a little bit later on. I want to finish out all the states of matter targets, because that's officially part of the gas law target. So that's kind of the part 2 stuff. So I will get to that here in a little bit. Okay. All right. So really, then the last part of the states of matter stuff here is the last target. We can skip target number 8. That's a laboratory target. We already did that. So target number 9. In terms of molecular motion, explain the relationships between temperature, volume, pressure as described by the following gas laws. All right, so remember, there are 4 variables that affect gas behavior. There's pressure, volume, temperature, and number of moles. Okay, pressure is measured in either atmospheres, which is ATM, or millimeters mercury, mmHg, or kilopascals, which is kPa. Temperature is measured in Kelvin. Volume is measured in liters or milliliters, and then you've got moles, obviously, which is measured in moles. Okay, and so we need to take a look at the relationships between all of these variables. Okay, so there is actually, of all the relationships that we studied, there is only one that is inverse, and that is pressure and volume. Pressure and volume is the only inverse relationship. Okay, if you think about picking up like a soccer ball or a basketball or something like that, right, and you try to squeeze it, what you're doing is you're decreasing the pressure on the inside of the ball. I'm sorry, you're decreasing the volume on the inside of the ball, and it gets harder and harder to squeeze it because the pressure is increasing. In the tutorial video that I did for that one, that's the one with the marshmallow inside the syringe. And so as I increased the volume on the inside of the syringe, the pressure went down, thus allowing the marshmallow to expand. Right? So there is an inverse relationship between pressure and volume. And as such, or since it's an inverse graph, what that means here, and let me draw this out for you using my little marker board here. This right here, this is an inverse graph. Okay, it's a negative curve that always stays positive. It is not indirect, it is inverse. So yes, pressure and volume is the only inverse relationship. All the rest of them are direct. Okay, so volume and temperature is a direct relationship, which should make sense because that's a hot air balloon. You increase the temperature on the inside of the balloon and the volume increases. Okay, so that is a direct relationship. Pressure and temperature is an inverse. I'm sorry, I'm getting all confused. Pressure and temperature is a direct relationship because if you increase the temperature on the inside, like say of a soda can, right, the molecules are moving faster, which means they're going to run into each other more often. They are going to collide, which causes more pressure. And so the demo I did for pressure and temperature is the soda can that got crushed because we changed the temperature so rapidly it dropped the pressure, which then also collapsed the can in on itself. Thank you. I appreciate you liking my background. This is my special room of creativity. This is actually where I do all of my music production and music writing and all that good stuff. So it sufficiently stimulates my creativity in here. So getting back on topic, a direct graph, and there is a reason why I am showing you this. Okay, you guys do need to know what the graphs look like. Okay, so here's your direct graph, right? It's just a straight line that goes up. Okay, all right. Hey, cool. Hey, thanks for the shout out on the band. It's a fun project. It's a very hard project, but it's very rewarding to do something so different. Okay. All right. So where was I? So we talked about pressure, temperature, volume, and temperature. Pressure and volume is the only inverse relationship. Volume and moles is a direct relationship, right? That's just blowing up a balloon, right? You take the balloon, you blow it up, you're adding more moles to the inside of the balloon, volume increases. Okay, so nothing groundbreaking there. So those are the relationships, okay? So you got to know whether they're direct or inverse. You got to be able to look at a graph and identify, what's going on with that. So now let's actually get to the stuff that most of you are asking about, which are the calculations. Because if you look over at the gas law targets, that's basically what all the gas law targets are. There's use the combined gas law, using the ideal gas law, and then using the gas stoichiometry, and then there's also Dalton's law of partial pressure. Okay, no, you do not have to identify the law on the test, because I mean, knowing the names of the laws, I mean, yeah, that's, I don't know, makes you sound scientific, but the whole point of, okay, dude, seriously, that's not cool. Okay, we are going to, yeah, we can't use that, and we're gonna get rid of that. Okay, thank you. Let's actually be polite here. There's no reason to use language like that. That's not cool. All right, so where was I? All right. All right, sorry about that, guys. Will I have tutorials tomorrow? As much as I would like to, we have a department meeting that got scheduled for tomorrow morning, which is part of why I'm doing this live streaming session right now. I will be available from 7:45 to 8:15 in the morning. But at 8:15 I got to be at and actually all of us will have to be at a meeting, so unfortunately, and no tutorials at 8:15. Okay. Okay, so let's start with okay, so I see we have a question for doing Dalton's law of partial pressure. Okay, so again, you will have a reference chart as you take the test. You don't have to have any of these formulas memorized, but you do need to be able to know how to actually use them. Okay, so for Dalton's law of partial pressure, let me write that out here. Let me use a different marker. This one's kind of going bad on me. So we got the total pressure equals the pressure of all of the individual gases added up. Okay, so like this, right? So you got your total pressure equals all of the individual gases all completely added together. Okay, so if we had something like, I'm totally making this up off the top of my head. Let's say you've got a system that is comprised of carbon dioxide and water vapor. So let's say the total pressure is, say, 1.2 atm. Okay, so that's our total pressure, 1.2 atm. And let's say the pressure of the carbon dioxide is 0.78 atm. Okay, and I want to know what's the partial pressure of the water. Well, all you're simply going to do is the 1.2 minus 7.8, 1.2 minus 7.8. Okay, like so. I'm not 7.8, I'm sorry, 0.78, if I can remember my own made up numbers right there. Okay, so yeah, so you just subtract them out. The only thing that makes the Dalton's law questions somewhat challenging is if the units, the pressure units are not the same unit. Okay, so let's say, for example, let's say stay with the 1.2 atm for the total pressure, and let's say the other partial pressure was 502 millimeters mercury. Okay, so something like this. Okay, then what you'll have to do is you convert the millimeters mercury into atm, and those conversion rates are on the reference chart. Okay, so what you'll do is 502 millimeters mercury over 1, and then since we know that millimeters mercury is on top, that means it's got to go on the bottom of the other fraction, like so. And then you just plug in the numbers like you find on the reference chart, which is 1 and 760. So you do 502 divided by 760, and then that's your answer. Can I do number 9 on the gas stoichiometry worksheet? I could if I had it in front of me. I'm so sorry. As I was trying to kind of remember to get all of my materials, there were a few things that I accidentally left in my classroom, so that's why I'm kind of having to go on. Did the audio cut out? No, according to everything I've got, my audio is still going good. Okay, so where did the 760 come from? Good question. That is the reference chart. So your rates that allow you to convert between the units, and I'll write it out here for you guys, is 1 atm equals 760 millimeters mercury, which is also equal to 101.3 kilopascals. right? So 1 atm equals 760 millimeters mercury, which equals 101.3 kPa. Okay. Okay, so we got a question. Could you go over how liquid, gases, solids, and vapor do certain things? For example, which of the following is empty space? Which one compresses? Ha ha. Very funny. Vapors. Okay. So I covered that right at the very beginning of the stream here. Basically, gases are the only ones that you can compress. Solids and liquids you cannot compress. And gases are the ones that have empty space. That's why you can compress it, but solids and liquids don't do that. So if you want more information about that, you can actually, what you can do is you can rewind the live stream here and kind of go back to the beginning. You can find that, or you can just go find the actual tutorial video that I made. That one's already posted. I believe that one is called something like I don't remember. It's the very first one, like the trifecta, solid, liquids, and gases, or something like that. Okay. Okay. So that is Dalton's law of partial pressure. One of the other equations that you guys need to know is combined gas law. So that is P1 V1 over N1 T1 equals P2 V2 over N2 T2 right here. Okay, so this is your equation. I know it looks like a lot, but here's the really cool thing about this particular equation. You can basically use this to go over everything. Okay, now before I go any further, and actually I'm just about to answer your question. Okay, you know how to use, or you know to use the combined gas law when the question has 2 of every variable. Okay. How different is the test from the Kahoot quiz? Well, the style of questions are the same. They're not all the exact same questions, but and obviously it's longer than that because the Kahoot quiz is only 15 questions. This one's got 33, but essentially it's the same style of questions. Okay. All right. So here's the equation. You know to use this one when there are 2 of everything. Okay. So even if it's only 2 pressures and 2 volumes. Okay. So basically what that means is you're going to cover up the bottom, and it's P1 V1 equals P2 V2. Okay. If you want to do say pressure and temperature, okay, so you're going to cover up moles and you cover up volume, and so you got P over T. Okay, guys, let's not have conversations about that. I may need to block some of you guys if you're going to have conversations like that here on the channel. Okay, so let's kind of focus on the chemistry. So let's say you got a question that has pressure, volume, and temperature. Okay, so you cover up moles. It's P1 V1 over T1 equals P2 V2 over T2. Okay, so all you got to do is you read the question and you plug stuff in, and then you kind of solve from there. So what I'm going to do here. No, it's all, guys. Okay, seriously, we don't need to be talking like that. Okay, that word is completely offensive, and I will not stand for that here on my channel. Okay, so that either needs to go away, or I will block you. Okay, that's your only warning that you're going to get about that. Okay. Okay, so I'm going to make up some words there, or I'm not make up some numbers to just kind of show you how to calculate it. Okay. So let's say we've got a pressure of, wow, this one's kind of running out on me too. It's a good thing I brought home 4 markers. See, this I did remember to bring home. Okay, it's all good, dude. Just gotta make sure that I'm clear on that. Okay. So let's say we got a pressure of 1.1 atm. We have a volume of say 0.5 liters, and we have a temperature of 300 Kelvin. And then we've got over on the other side, let's say we have a new pressure of 0.78. Volume 2 is what we're looking for, and we have a new temperature of 273 over here. Okay, so let's say that this is what we're trying to solve for. There are a lot of different ways to do this, because basically at this point this is just an algebra problem. So if you want, you can combine all these terms, combine these terms, and then do your division like you normally do. But what I like to do is kind of a one-stop shop kind of thing. I put it all in the calculator. I do it all at once so that I don't have to round as I do this. So what I will do is I will do some cross multiplication, and you'll see that there are two diagonals, right? You got this diagonal right here, the 273, the 0.5, and the 1.1. This basically is all three numbers, and then you get your other diagonal, which is 300.78, and then your missing variable. Okay. Yeah. So this is combined gas law. Sorry, I missed that question. So two diagonals. Start with the diagonal that has all three numbers. Okay. So what I'm going to do is I'm going to multiply. I'm going to do 273 times 0.5 times 1.1. Okay, that's essentially what I'm going to do. And then I'm going to hit the equal sign. So basically what I'm writing out is what I'm typing into the calculator. So 273 times 0.5 times 1.1. Then what I'm going to do is I will divide by the other two numbers individually. So I will divide by 300. And then I'm going to hit the equals. Okay? Then I will divide by 0.78 and hit the equal button. Now, it works exactly the same way. Okay? All right. Blocking you. Not cool. All right. Sorry about that, guys. All right. I'm trying to get things back to where I can see everything. All right. Okay, cool. So to kind of recap that right there, we've got 273 times 0.5 times 1.1 divided by 300 divided by 0.78. Okay, and that's how I would solve that. Let's say, for example, if I move the missing variable somewhere else. Okay, so I'm going to keep some of the same numbers here just for the sake of argument here. Let's say I've got 9.78, 9.75, and 273. Okay, let's say we have something like this. Okay, okay, our N and T inverse. I'm also confused on how you can find what equation to use. So technically, yes, moles and temperature are inversely related. But that's not one of the relationships that we studied, so I really wouldn't worry too much about that. But how do you know which equation to use? Well, this one's combined gas law, and you know to use it when there are two of every variable. So if the question gives you two pressures or two volumes or two temperatures, whatever it is, that is combined gas law. If you are dealing with only one of every variable, that's going to be the ideal gas law. That's PV equals nRT, or PUVNRT, as I like to call it. And then if it's only dealing with pressure, that's Dalton's law of partial pressure. Gas stoichiometry happens only at STP. So I'll do an example of that here in a little bit as well. Okay. So back to this example right here. So again, we have two diagonals. We have this diagonal, which has all three numbers, and then we have this diagonal, which only has two numbers because it also has the variable. So again, I'm going to start with the diagonal that has all three numbers. So I will do 273 times 0.5 times 1.1, and I'm going to hit the equals. And then I will divide by the other two numbers. Divide by 0.78 equals. Divide by 0.75 equals. Okay? Now, again, you can do it using the, the algebra that, that you've learned in your algebra class, and then, do each step individually, round at each step, and then move on. But what I find, though, is that if you're rounding at each step, then your number is not going to be the same as the number that you'll see in the multiple choice, and sometimes you get a little confused like that, which is why I like to explain it like this and kind of just do it all at once, and you do the calculations like so. Okay. Okay. Can you do a problem where you give us the values and we plug it in and you give us the answer so we can see if, okay, that's actually a really good good suggestion. Okay. And I will do that at the very end. Okay, because I want to finish kind of explaining all the different equations. Hope that's okay. All right. So so that's combined gas law, and then we've got PV equals nRT. All right, we got Puvnert. You know that this is the equation that you need to use when you are given one of everything. So one pressure, one volume, one moles, one temperature. Okay. R is the ideal gas constant, and that number is on the reference chart. You just got to make sure that you're picking the R that matches up with whatever value for, I'm sorry, whatever unit are used for pressure, whether that's ATP or, sorry, ATP. That's biology. A flashback to biology there. ATM, and then, or kilopascals or millimeters mercury. Okay, so that's ideal. Combined, you got to have two of everything. Now, gas stoichiometry. Let's say we have this equation. I'm going to use a pretty simple one. Okay, so 2H2 plus O2 gives us 2H2O. Okay, yes, temperature has to be Kelvin. Always Kelvin. All right, so let's say we're using this, and there's basically three different types of questions that I could ask you with this. Okay, first question, we do a liters to liters conversion. Okay, so let's say I have 25 liters of H2, and I want to convert that into liters of oxygen. Okay, like so. So this is where we're going to do a liters to liters conversion using the coefficients here. Sorry, I'm going to get that back on the camera. Using the coefficients here in the equation. Okay, so I'm going to take 25 liters of H2 over 1. So liters of H2 is on top, which means liters of H2 goes on the bottom. What I'm looking for is liters of oxygen. That goes on top. And so now I'm just going to take the numbers straight out of the equation. That's 1 liter, and that's 2 liters. So this is going to be 25 divided by 2, which is 12.5, and then your units are liters of oxygen. Okay, so if you're doing a liters to liters conversion, you are simply going to take the coefficients out of the balanced equation, just as if you were doing a moles to moles conversion. It's exactly the same process. You're just using liters instead. Okay, but what if? So once again, I'm going to start with 25 liters of hydrogen, and this time we're going to go to moles of oxygen. Okay, so this is a liters to moles. Okay, so what I'm going to do is first we got to do liters of hydrogen to moles of hydrogen, and this is where we use the 22.4 liters per mole. This is what has to be done in order to convert liters to moles. So I'm going to set up 25 liters of H2 over 1 times, and then so liters of H2 goes on the bottom with moles of H2 go on the top, and we have 22.4 liters per 1 mole. Again, you don't have to memorize that particular value because it's going to be given to you, but again, you have to kind of know how to use it correctly. Okay, so you got to match it up with liters. It's 22.4 liters per 1 mole. And now that we're in moles of hydrogen, we'll do a moles to moles conversion, just like we have, like we've done before using our balanced equation, okay? So moles of hydrogen here, moles of O2 here, and I can see I got 1 mole of oxygen for every 2 moles of hydrogen. So you'll do 25 divided by 22.4 and then divided by 2, okay? So that is a liters to moles conversion. Then the other way that I could ask this to you is the exact opposite. So I'm going to start with the same number. I'm going to start with 25, but this time it's going to be 25 moles of hydrogen to liters of oxygen, like this, okay? So this time I'm going to, same process, I'm just going to flip it around a little bit. So I start with the 25 moles of H2 over 1 times, and then so I got moles of H2 on top, which means moles of H2 goes on the bottom, moles of O2 on top. I take my numbers from the equation. That's 1 mole, and that's 2 moles. And now that I'm here, I'm going to convert into liters using the 22.4 liters per mole. So that's liters, and that's 22.4. Sorry, I'm getting a little crushed here. I kind of ran out of space since I used too much over here. Okay, so I know that's kind of hard to read. I know I did that. Okay, you're gone. Okay. All right, sorry about that, guys. Apparently some people just don't understand how to behave themselves in civilized circles. All right, anyways, it's all good. It's all good. We're not going to stop. All right, so to sum up, so moles to liters, this is moles of hydrogen to moles of oxygen using the balanced equation, and then you multiply by the 22.4 liters per mole. Okay? So 3 different ways on how to do that. So if you want to see that again, obviously you can just kind of rewind this particular video, or you can go find one of the other ones where I talked about the gas stoichiometry and showed you how to do that. Okay, so those are the 4 main calculations that you will have to do. Okay, so we had a question: are you going to have to find molar mass on your own? You know what? Honestly, I don't remember. If I remember correctly, I think we guys give you the molar mass because that's not really the focus of this particular test. But at the same time, it is something that we've already done. So you should be prepared to, take your periodic table and find the molar mass and add it all up. Okay. Why do you need to do the balanced equation part? So you need to do the balanced equation part when, so two reasons. One, if it's a liters to liters conversion, you are using the balanced equation to do a liters conversion, okay? Because you can just kind of do that in one step. The second way to do that is when you're doing a moles to liters or liters to moles, and that's the moles to moles conversion. So the balanced equation comes out when you have to do moles to moles conversion. Because if you just do times the 22.4 liters per mole, but you haven't converted the substance yet, then you're not actually doing a really good comparison. So that's why you got to use the balanced equation. Okay. Okay. So how do you convert the different types of pressures into each other? And the equations. Okay. And that I can show you. So let's say you are given 75 kilopascals. Right, and we want to convert this into millimeters of mercury. So if kilopascals is on top, it's going to go on the bottom over here, and millimeters mercury is on top. Okay, and then so we just take the numbers, which is 760 for every 101.3 kPa. So to answer your question of how do you know if you multiply or divide? Well, once you have it set up like this, right? So you've got your units all in the right places, and then you got the numbers matched up with the right unit. If the number's on top, you multiply. If the numbers are on bottom, then you're going to divide. My goodness. Okay, so we got some people who are trying to spam us. Lovely. Okay. Very nice. Okay. So to answer your question, if the number's on top, you multiply. If the number's on the bottom, you're going to divide. Okay. So we're going to wrap up here real quick. We're almost at the hour mark. So what I'm going to do is I'm going to give you guys some questions, and I want you guys to try and work them out on your own. We'll compare answers. And so we'll probably do 2 examples because I think that's really about all the time that we have, and then we will do that. So yes, I would appreciate help with modding the chat. No, it's all cool. It's all good. Oh, good. See, I can't even talk right now. It's late for me. But yeah, we'll figure this. I mean, this is only the first time that I've ever done this live stream, so obviously there were going to be some hiccups along the way. We'll figure it out in the future. Okay, if we ever do this again. All right. So example questions. All right. So let's say. All right. I'm gonna try to write something out here. Instead of giving you a word problem, I'm just gonna write out some stuff here, just kind of make it easier. So we have a pressure of 1.2 atm, a volume of 0.63 milliliters, and a temperature of, let's say, 18 degrees Celsius. And then on the other side, we have a second pressure that has changed to, I'll show this to you here once I'm done writing this out, 0.75 atm, and volume 2 is going to change to 1.3 milliliters, and we want to know, okay. Okay. Yeah, you guys are welcome. It's all good. So you guys, you know, I appreciate those of you that are hanging with me, that are actually here for chemistry reasons. So it's all good. It happens. Sometimes you got to learn how to deal with rude people and just kind of move on. Don't let it bother you. Just move on with your life. All right. So anyway, so here are some numbers. So write them down. Okay. Hopefully. Okay, for this particular one, since we got 2 of each, this is combined gas law. This one can be in milliliters. If there's 2, then as long as it's the same on both sides, it really doesn't matter. It's only for Puvnert. Then yeah. Okay, so if you want to convert, I mean, you're welcome to convert it into liters if that's what you want. So if it starts with milliliters, divide by 1,000, that gives you liters. Okay, or if you have liters, multiply by 1,000, that gives you milliliters. But like I said, as long as it's the same on both sides, it really doesn't matter. It's only for Puvnert that the volume has to be in liters. Okay. Okay, hopefully that's been up long enough for you guys to have written it down. We got somebody else. Yay. All right, so you guys work. I'm gonna try to write this out and we will compare answers here. All right. So hopefully you guys are working on it. I'm trying to get my my stuff right here. Sorry, I'm trying to use my, I don't have a calculator, so I'm using the accessories calculator on my desktop here. Yeah, thanks. Beer is awesome. You should check out the video I did about my 10-year beer anniversary. That was actually pretty fun to do. The heat graphs. Don't worry about sig figs. It's a multiple choice test, so I'm not really going to worry so much about that. All right. So what I've got here, 300 and. All right. So here is what I've got. Sorry, let me bring this up. Okay, there we go. I've got 375 Kelvin, which of course then you can subtract 273. Yeah, immaturity is just kind of comes with the game. All right, so 273. I'm sorry, 375 minus 273. So that would be, looks like 102 degrees Celsius. All right. So do I need to explain how I got that one? You got 373. Well, that may be how you rounded, which is what I was talking about. You know, if you kind of stop partway in between, your answers can get off a little bit. So what I did was, so the three numbers that are all there together is 291 times 0.75 times 1.3 equals divided by 1.2 and then divided by 0.63. At least that's how I should have done it. Let me double check. Now that I'm getting confused because I had to. Yeah. Sorry, I got confused, or not confused, but I got distracted by all the lovely comments happening here on the side. So let me try that again. All right, so 291 times 0.75 times 1.3. Multiply that out, and that equals 283.725. And then I'm going to divide by 1.2. Oh, I got a decimal too. Okay, it's all good. And then divide by 0.63. Yeah. Okay, so confirmed it again. So it ends up being 375.2976. Blah 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 blah. Okay. It's all good. That's actually kind of that's a funny little typo right there. Okay, so let me explain that again. So what I did in the calculator was 291 times 0.75 times 1.3 equals, divided by 1.2 equals, divided by 0.63 equals. And what you get is 375.2976, blah, 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 blah. Then you subtract 273, and then that equals 102 degrees Celsius. Okay? So that's how that one works. Do you have a trick to remember to always add 273? Well, the trick is just to kind of get in the habit of every time you see Celsius, just add 273. You know, I really don't know how you would have gotten a number so large. The only thing I can suggest is go back and try it again the way I just suggested it. So the 291 times 0.75 times 1.3 divide by 1.2 divided by 0.63 and see if you get the same thing. You should get the same thing that I did. If you're still having problems with it, I guess in the morning, if you're able to come up a lot earlier, like say around 8 o'clock or so, I mean, I'll be available. But like I mentioned earlier in the stream, we have a department meeting at 8:15, so unfortunately I won't be available. Okay, so do you always need to subtract 273? It depends on what the question is asking for. If all the answer choices are in Kelvin, then just leave it in Kelvin. But if all the answer choices are in Celsius, then, well, then yes, you would need to subtract 273, okay? No, you don't need to do R for this because this is combined gas law. R comes in the ideal gas law, okay? All right, so we're gonna wrap up here with one last question. We've already been going for over an hour here. And I would also like to have a little bit of time in my evening. So we will do one last question, and then we will call it a night. Okay, so I appreciate you guys logging in and sticking with me for the duration here. Looks like actually most everybody's still sticking around here. All right, so let's say that we have a pressure of 0.87 atm, and we want to know what the volume is, and we have 3.0 moles, and the temperature is, say, 20 degrees Celsius, like so. Okay, so pressure is 0.87 atm. The volume is what we're looking for. We have 3 moles and a temperature of 20 degrees Celsius. Okay, so this is one of each. And so this is obviously going to be Puvnert, PV equals nRT. Will I do more live streams? Possibly. I mean, this is the first one that we've done. So hopefully, for those of you that have logged in and are checking this out, hopefully you guys are getting some good help with it. So if there's a lot of really good positive feedback about this, then yeah, I will definitely do more live streams. Okay. So here we go. So these are the numbers, like so. You guys have them written down, hopefully at this point. Oh, that is a good question. If you probably don't have the reference chart in front of you, R for ATM is 0.0821. R is 0.0821. So there you go. Yes, yes it is. Okay. All right, so I'm gonna work it out. You guys work it out, and let's see what happens. All right. Okay. Bring up my little calculator here. Okay. Hopefully you guys are ready. Maybe I should give you a little bit more. I don't know. If you really want more time, I guess you can just pause. Start again. Okay, so here we go. This is what I've got. Okay, so this is PV equals nRT. So P is 0.87, V is what we're looking for, N is 3, R is 0.0821, and T is 293, right? Because that's 20 degrees plus 273. Yeah, and that's what I got. So you calculate all that out. What I got was 82.949, blah, 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 which I then just rounded to 83. And since this is volume, the units are liters. And remember, this is Puvnert, so the volume must be in liters. It is definitely not milliliters for this one. Okay. Wow, if you got a number, okay. Here's what I'm betting you did, possibly. You probably kind of divided the wrong side. Since you're trying to get volume all by itself, you need to divide both sides by 0.87. You don't take 0.87 divided by all of this, okay? So let me kind of go back over this one real kind of slowly just to make sure that everybody understands what's going on here. So our equation here is PV equals nRT. P is 0.87, right? Pressure is 0.87. Volume is what we're looking for. Moles, N, is 3. R is the gas constant, and since pressure is in ATM, it's 0.0821. Temperature is 20 degrees plus 273 to get 293, so we plug it in there. And so in order to get volume all by itself, I'm going to divide both sides by 0.87. So I will start in the calculator by doing 3 times 0.0821 times 293, and then you divide by 0.87. Okay, and that's how that one is done. When will I be available tomorrow morning? I will be available from 7:45 to 8:15. And I'll be sure to let the people downstairs know to let you guys up if anybody's wanting to come in. Unfortunately, we have a department meeting. I know it's terrible timing. I didn't schedule it. We have a department meeting at 8:15, so I have to go to that. So I will make myself available from 7:45 to 8:15 for anybody who wants to come on in. Looks like the next question is if the PV nRT question is asking for temperature, what do we do with the Kelvin part? No, Alec, I cannot give you a ride home. Sorry. I know that's a lifelong dream of yours. The answer is no. What do you do with the Kelvin part? Okay, so when you solve for it, you are going to, obviously it'll be the number value you will get will be in Kelvin. This is multiple choice. So if all the answer choices are in Kelvin, then leave it. But if the answer choices are on Celsius, then yes, you'll have to subtract 273 in order to get that, okay? Okay, so this will be the last question that I will take here. So it says on the reference sheet, it says R is 0.0821, 8.31, or 62.4. How do you know which number to use? That is an excellent question, and it all depends on the unit of pressure. Because if you notice on the reference chart where it says, it's kind of hard to see there, where it says 0.0821, if you'll look over there, the unit of pressure right there is ATM. So 0.0821 is used when pressure is measured in ATM. 8.31 is used when pressure is kPa. And then 62.4 is used when pressure is measured in millimeters mercury. Okay, so that's it. I want to thank you guys for being here for this inaugural live stream event. I hope that was really helpful. I really appreciate you guys sticking around for the hour and 10 minutes. So this has been a great time. I appreciate you guys and I appreciate your patience on all the other people there making some inappropriate comments, and that was lots of fun, right? So just another good story for us to tell. So you guys are rock. You guys are awesome. I love you guys. I will see you guys tomorrow. So remember, I'm not Dan, and neither are you. All right, so check you later. See you guys.